Okay. Uh, yeah, we have only two topics: stress and strain, and elastic and plastic behavior. So before that, we will just recall what we have learned in last chapter about forces, energy, and density, pressure, everything together. Okay. So do you understand that we did something called rigid bodies, like the distance between the atoms or molecules, they do not change. Okay. So now this chapter we are interested in what if it is not a rigid body. Okay, so remember in the first chapter, we were merely talking about a particle, and second chapter, what happens to its velocity. Third chapter, what happens to its acceleration or what is the energy behind it. Fourth chapter, what happens to pressure and density. Fifth chapter, what happens to the energy and work done. Okay, so now, so the second aspect of the force. So if you are applying force to an object, what if the velocity is not changing, but the system inherits the force and some change it happens to the system? So this is what we are interested in this chapter, deformation of solids. Okay, you should understand by deformation meaning that whatever the force we are applying is not directly translated to change in velocity, but change into shape and size of the object. Okay, so this is what our theme in this chapter. Yeah. So before that, so we want to understand what are the types of forces. Okay. So from checkpoint to IGCSE, we know that push pull is the type of the force. Um, so this push or pull are very seems like very vague term, but they have clear effects on the body. For example, let's say that I have a cardboard box. Okay, and this cardboard box is on the ground or something. Now, if I push, now if you look at these two sides, okay, this and this, let's say that they can tolerate the push, then the box will move in this side. Okay, so remember that we are talking about cardboard boxes, but instead of pushing, if I pull, there is a possibility that this side alone can break and come with our hand. Have you noticed some signs that only push, no pull? Yes, so this is the reason. And so for example, one more day-to-day life example is train. Okay, so normal Indian trains, they will have only engine in the front, and they have to pull all the cars from the back. Okay, so there is a limitation how fast this train can accelerate, because if it accelerate all of a sudden, then the chain between them is not enough to hold all the car throughout the acceleration. So that's why their accelerations are very limited. But if you want faster acceleration, such as metro or EMU or recently launched Vande Bharat trains, then what you have to do, you have to distribute the force throughout the train. So that's where we call it as a EMU, electrical multiple units. So what you will have a car. So all of a sudden you will have a motor, an engine. So you distribute the force throughout. So you can have faster acceleration and deceleration. That's the idea. Okay, so so this is the main theme of this object. So what happens to the force if velocity is not the one changing? Okay, that's the idea. Yes. Now let's take an object, and this object is not perfectly rigid body, meaning that if you apply force, it will deform. Okay, so now if we push from both side, what's the resultant force? Equal amount. So if let's say that we are pushing from both sides with equal and opposite forces, what will be the resultant force? Zero. So the velocity change in velocity will be zero. But this force have to work out somewhere, right? Clearly, we are applying force. The velocity is not changing. So where it will work out? In the center on the box. Okay. So what will be the result of this force? So this is what we call it as a compressive forces. Meaning that you are pushing an object at least from two sides, but you can push from any more number of sides. But in order to get a compressive force, you need to push at least from two sides. Okay. Now let's reverse the scenario that you are pulling from both sides with same magnitude of force. Now what will be the resultant force? And what will be the resultant force? Resultant force will add it up with respect to the box. But if you observe velocity of the box, it will be still zero, change in velocity. So resultant force with respect to the surrounding is zero, but the forces will result of stretching the object. So this is what we call it as a tensile force. So compressive forces and tensile forces. Okay. For depressed tensile force also it's zero, but the object deforms. Okay. So to make the study easy, we will limit our situations only to one dimension. Okay, so it's easy for us in ASI level. But if you choose mechanical engineering or civil engineering, you will learn about what are the effects of. There are different type of tensile forces, compressive forces also. For example, buckling, knuckling, and then you bend. So there are different forces. Okay, yeah. So this is the idea we want to study. Now that's why if there is a rope and then you are pulling in this end of the rope with F, and this F is working on the rope by the tension force. That's why we call it tension is also a force. Okay, so we might have wondered the rope is not moving at all. It's not changing velocity. How does this force work? This force work as a tension. Okay, so uh, let's say that we are pulling this box with force F. Okay, clearly the box is moving. So the box has been shifted from original place to somewhere else. So clearly we can see the force, but the rope's ends are not changing, right? They are in fixed distance. So no change in velocity between the end of the ropes. So how we can assume there is force exerted? Because force exerted as a tension. Yes. So that's why tension is a force. Okay. Now this is a basic idea, fundamental idea. Now to study this chapter, tensile force means that you are stretching an object. Tension also one of the tensile force. Okay. Tension maybe you can understand this. Tension mean the rope is stiff. Okay, if there is no tension in the rope, no stiffness. Okay, let's say that you are pulling with F, but the rope look like this. Will it change velocity to the velocity of this box? Because whatever force we are applying not enough to stretch this rope. So only when it is completely stretched, the rope is no longer extending, then this will transfer the force to the box. Okay, yes, with the tension. That's the idea. Okay, if you watch Bahubali movie, this Bahubali guy will be pulling the rope, okay, of this big statue, but the rope will look like this. No tension between the force. That's a movie mistake. Okay, so because such as the rope, if it can hold such mass weight, it should be straight. Yes. Okay. So that's the idea. So to study about this deformation of solids, we need to understand some fundamental terms. Okay, that's what we are going to learn here. So they are these fundamental terms are so load, extension, compression, and limit of proportionality. Understanding of these terms are very important. Yeah, okay. First, we will understand what is load. Load is nothing but force. Okay, so you can provide load by different means. For example, you take a wire and then hang a mass to it. So gravity will act as a load. Okay. So you hang a wire and then literally you pull it. This is also a load. Load is nothing but force. Okay. As usual, we always should try to accommodate the resultant force. Okay. So that's very important. Yes. So now then what is extension? I think this word carries the literal meaning. So extension meaning, what is the original length? Okay, let's take this is L. And once we apply some load, then it extended by this amount. Can you see? So this is what we call it as extension, usually denoted by letter X. So whenever they say extension, this is not the original length. It's a difference in length when force is applied. That's very important. Is it clear? Yes. Yeah. So that's extension. Similarly, compression is opposite. For example, this is the original length. Let's say that we are pushing so that the lengths become little shorter, and this is compression. Okay, both extension and compression are denoted by the letter X. Oh, I see. Okay. In strings, it will not occur. But let's say that you take a rod. Okay, you take multiple rods and put cement around them. Then this become a pillar. Once you make the load on the top, then they will compress in one axis. Yes, yes, yes. Mm. Okay, so that's the idea. Now the limit of proportionality, we have to deal it little carefully. Okay. Now what is limit of proportionality is so let's say that I have a wire whose original length is L, and if I hang a load, then it extends to delta L. Okay. And let's say that I if I remove the load, it should come back to original length. So until for which load it can come back to original length. That's what we call it as limit of proportionality. Okay. For example, let's say that if I apply too much of load, okay, so that this has extended this much, delta L. Even after I remove my load, it does not exactly come back to L. So meaning that we will say that the object has crossed the limit of proportionality. Okay. So we can make this with a graph so that it's very easy to understand. Okay, let's say that we are applying load and here is the extension. Okay, until some point, even if you remove the load, it will come back, but after some point it will not come back. The extension remain same even if you remove the load. Okay, that's the idea. uh, yeah, so that we have in the next part. Okay, and so actually this graph is little complicated, but I'm just leaving it now, so we'll discuss in next one. Okay, so here is the limit of proportionality until where it is a straight line. Okay, 1 minute, sir. I'll check the axis. Yeah. Okay, now so until which, even if you remove the load, so can you see that this part is linear? So until which it remove the load, this is the region we call it as Hooke law. So what is a Hooke's law? Yes. So the force is directly proportional to the extension, to limit of proportionality. Okay. So the detailed version of the law is this: the force needed to stretch or compress elastic material is there. No, you can just directly write force is proportional to extension. But the idea is this: the force needed to stretch or compress elastic material is directly proportional to distance it's moved from original position. So the difference is what we call it as extension, right? Hmm. Okay, so this is Hooke's law. Now, um, so we'll take a different material. Okay, load and extension. Okay, one material will go like this until Hooke law only we are talking. Okay, let's say this is material A, and another material can go like this. This is material B. Another material can go like this. This is material C. Maybe we'll have one more material, material D. Okay, out of this A, B, C, D, four materials, which material extend large for a smaller force? C. Yes. Okay. So then we call this as more elastic material. Mm. Uh, but this is not rubber, because rubber is not a straight line. You should not confuse with this rubber. A good example is metals. Okay. Particularly gold. Okay. For example, uh, uh, do you remember from IGCSE this Rutherford gold foil experiment? Okay. Yes. So have you ever wondered why they chose gold? Yeah, because gold is very malleable. Okay. You can just take 1 gram of gold and stretch into 50 meter of wire. So that's much malleable. That's why they can give or embed good designs in the gold ornaments. If you make with the same design with let's say ever silver, or even silver can hold up to some steel, if you take, then it will bend easily. The gold will stay for longer time. Okay. Mm. Yes. How about material D? Yes. So still it is elastic, meaning that if you take the extension, take the load, it will come back to original position. Okay. A very good example is a glass or a rock. Okay. Can you see that concrete is a good example? Heavy trucks are passing by, but extension is very small. But once the truck pass by, they'll come back to their original position. If they don't come back to original position, the material is no longer suitable for highways or bridges, right? Yes. So this is glass. Concrete is a good example. Okay. So this one is more elastic. No, limit of proportionality for, until which they are proportional to extension. Yes. More elastic, less elastic. Okay. Yes. So we identify that different material can obey Hooke's law, but how do they obey Hooke's law is different, right? What are the key difference between these lines A, B, C, D? Mathematically speaking. No, mathematically speaking. Okay. Okay. Tell me the force applied. Hmm. So in other words, yes, gradient. In other words, if I apply the same force, this will extend the least and this will extend the most. Yes. So the mathematical difference is gradient. So now the gradient in this graph is so this is theoretically extension by load. Okay. But since they are straight lines, we are more interested in load extension graph than force extension load graphs. Okay. Can you say I just switched axis? Then T will be here. Uh, A will be here, B will be here, C will be here. Here what I'm going to do, instead of applying load and checking the extension in this graph, I will try to calculate for this much extension how much load I should put. Do you understand the difference, sir? Yeah. So that's the idea. For this much extension, how much load I need. Okay. So here the gradient is load by extension. Okay. So we call by these two graphs, we understand this load is proportional to extension, right? Yeah, we have. So sometimes they call it force, sometimes they call it load. Yeah. No, actually, this is we no, we can also extend here that this extension is proportional to load. Okay, both will give same results as long as they are straight. Okay. Yes. The results does not change. Only how we plot them changes. Okay. Now load is so you will understand in a minute why what is the use of this graph. Okay. Load is proportional to x. To remove the proportionality, we will introduce some constant. This is what constant we call it as a spring constant. Okay. So what do you mean by spring constant? So here also we could have introduced as 1 by k, but that's unnecessary. That's why I introduced this graph. Okay. Now, so what is this spring constant talks about is, if you give load, how much proportional, by what proportion the extension happens. Okay. For example, if you look at this graph, if I give, let's say, load one time, the extension happens at 0.1 time. For this graph, if I give load one time, extension happen one time. For this guy, if I give load one time, extension happens twice. Okay. So okay, the spring constant. So load equal to k into x. So if I give load, by what proportionality extension happens, that's the idea. Okay. So if the spring constant is higher, meaning the material is more elastic. For if I, let's say that if I give 1 Newton of load, by the way, before that, okay, do you understand? If spring constant is higher, the material is more elastic. It will stretch more for the same load. Okay. Can you tell me the SI base unit of spring constant and SI unit of spring constant? Yes. So SI unit is Newton meter minus 1. So it can be centimeter or meter, no problem, centimeter or meter. But I asked for SI units. Okay. So SI base unit is for spring constant, it is Newton meter inverse. Newton is kilogram meter second power minus 2 into meter inverse. So it will be kilogram second power minus 2. So that's a SI unit of spring constant. Okay. So just try this, make sure it's right. Okay, sir. So it's mass divided by time square. Yeah. Okay. Now the spring constant is a very important idea. In engineering, it's very important because different places you need different materials. Okay. For example, let's say, so what's the purpose of the material? That's a very important question. So for example, you might have seen, I don't know if you have seen this one, tempered glass. Have you seen? What do you mean by tempered glass? For we need the purpose is we need to protect the screen guard. Uh, so it should not shatter or it should not extend that much for a force that toughen the glass. So you need very low spring constant. Okay, but the idea is the spring constant does not tell you the story when the material will break, right? Yeah, yes. So super. We need to know the limit of proportionality. That's a very important idea. And for example, let's say that I want to construct a civil building or bridge. Should I have great spring constant or less spring constant? So even if we apply the load, it should not extend this much. So that's the idea. Okay. Yes. Okay. So okay. So now what about how we want to choose material for different occasion? That's a question. 1 minute, sir. So I have one more graph that not included in our syllabus, but this is very important. Yeah. Okay. Um, so we understand spring constant, sir. Is it clear? Yes, sir. So once we understand spring constant, limit of proportionality, extension load. So there are two more quantities. These are just properties. There are two more quantities that we need to calculate using this. So those are stress and strain. Okay. So this also we have to understand. So stress is nothing but pressure. Okay. Yeah. So stress is force by area. Sometimes this is the letter stress is given by rho or sigma, but you should look for what is stress. Okay. Strain is what is the ratio of extension and original length? Strain. Yeah. So delta L by L. So what is SI unit of stress? So it's pascals or Newton meter per minus 2. Okay. Work out for SI base units, sir. Meter inverse second per minus 2, I guess. Okay. Now what is a SI unit of strain? Top or yeah. So it's a dimensionless quantity. So its dimensions or units are 1. So it's a pure number. Strain is a pure number. Yes. Okay. It's gradient, sir. Gradient also will have the unit of the axis. Yeah, still it will have. For example, in this case, if you find the gradient will have the unit of force by extension, Newton per meter. Gradient is spring constant. So they will have. Yes, yes, yes. Okay, okay. Is it clear, sir? Yes. Now, this ratio of stress and strain is very important. That's what we call it as a Young's modulus. Okay. By the way, what do we mean by modulus is, okay. Yeah, yeah, yeah. No, we should not ignore it. There is a proper reason why we should ignore it. Okay. Yes. Okay. So Young modulus is ratio of stress and strain. Okay. Um, so ideally, so where does this Young's modulus come from? Is the stress is proportional to strain. Okay. So stress is proportional to strain. So stress equal to K into strain. This K guy is stress by strain. Yes, that's our Young's modulus. Why? Okay. So he will has the same unit as stress because strain doesn't have unit. So Young modulus also will have a unit of Pascal or Newton meter per minus 2. Okay. So if there is a graph, stress versus strain, the gradient is Young's modulus. Okay, sir. Is it clear? Yeah. So now that we understand stress and strain, remember stress comes from force by area. Strain comes from extension by original length. Okay. Now if you see, so in the material, will we change area of cross section? No. Will we change the original length? Can we change the original length? So this graph can be directly translated to force into extension. Yes. Now, but why, if this graph can be directly translated, what is the importance of this graph is, okay, if you take a wire of just 1 millimeter square cross sectional area, it will behave differently for different load. If you take the same wire with 10 millimeter cross sectional area, it will behave different for the different load, right? So what's the ratio? That's why this graph is important. You get the idea, sir? Otherwise, we do not need this graph. That's why study of stress and strain is important. Okay. So by this also, remember we ask a question. Despite of we know the spring constant, how do we choose material for different things? Okay. So that's why the spring constant information is not enough. You also need what is the width of the object, what is the length of the object. That's where this stress and strain graph comes into picture. Does it make sense, sir? Yes. Okay. So now we'll plot the same graph, but this time with stress and strain. Remember, sir, spring constant doesn't have any information about area of cross section or what is the ratio of original length to the extended length. So spring constant, if you think about it, it's an intrinsic property of a material. If you take unit area of cross section and unit length, then you can directly picture it. Otherwise, you cannot find the relevancy between what is the difference between 1 millimeter square unit or 10 millimeter square unit area. So, but this area will affect how the load is distributed, right? Okay. Is it clear, sir? Make sense? Yes. Okay, sir. Can we? Yes. Okay. Now, if we take a material, remember that this graph can directly translate it to force versus delta L, but we already discussed why that is not enough. Yes, sir. Okay. So now, as usual, we'll take. So until some point, stress will be directly proportional to strain. That point is what we call it as a limit of proportionality. Okay, here is a limit of proportionality. And then it will not all of a sudden will go. Okay, it will try to change little bit. Okay, there will be a curve. So even if you go to that point, you will come back, but not to your actual length, close to your actual length. Yes, close to original length. Okay, so this point is limit of proportionality. Yeah. So that's why I wrote F versus delta L also. Okay. Yes. Now let's call this A and this is B. So this is what we call it as a yield point. Meaning that until that you can go in extreme situation, you can go until that point. You will close to come back to your original length. But beyond that, you will not come back. Okay. Yes. So where you will not come back is the point we call it as permanent. Okay. Yes. So from that moment, it's no longer elastic. You will not come back to original point. Okay. So from this moment, see, we call it as a permanent set. It's the deformation is plastic, not elastic. Okay, sir. Yes. So and then the graph will vary depend on the material, but you have two more point. So and then so far most of the graphs will most of the material will follow the same graph. But until then, so this is a rough diagram. Okay. So this depend on the material. Okay. So you have two more point. So can you see that if you stretch more until then, even if you apply small force, it will stretch more. Can you recognize? So that point is what we call it as ultimate tensile strength. No, we don't have strength. What you mean is you will never going to come back to your original point. But until this, the material can stretch and hold. It can carry your load. Okay. So after that, what you will have? So that's what we call it as a fracture point. Okay. Now a question for you. The distance between D and E, do they have or do they possess any significance? Distance between ultimate tensile strength and fracture point. What is it? Yes. Super. Okay. Okay. Super. You are close. If D and E are closer, okay, the moment the material reaches ultimate tensile strength, if you apply a little more extra force, it will break. Okay. But if D and E are farther apart, okay, if they are farther apart, even if it reaches ultimate strength, it will extend like a rubber. It will not break like a sudden. Okay. So good example. If D and E are closer, you will recognize once I pronounce this word. If D and E are close, we call that material as brittle. Does it make sense, sir? If D and E are close, do you want to make the guess, sir? You are far away. What is okay. Ductile. Okay, that's the idea. Yes, yes. So why not? We don't have this in syllabus, but why we are asking this is this understand of D and E close or far apart is very important for the last section of the question. They will ask if we add extra forces, what will happen to the wire? Do you remember they will have a last part they from the graph? Yes, this idea is very important. Okay. Yes. So now um, we know that stress is it clear, sir? Yes. Yeah. Hmm. Limit until if you extend limit of proportionality, you will definitely come back to your original point exactly. But until yield point, it is close to straight line. You will come back to original point, but not exactly. But so beyond this yield point, you will never come back to your original point. No. Yield point, you will come close to your original point. Elastic point, you will never come back to your original point. Okay. If you go near or beyond C, you will never come back to your original length. The deformation is permanent. Okay. Yes, sir. So we know that stress is force by area. Okay. So if I have a wire, what is the cross section? Area of cross section is area. Okay. And this is the length, original length. And after we apply force, if it extended, this is the extension. Okay. Strain is extension by original length. And Young's modulus is ratio of stress and strain. Stress by strain. So it is force by area divided by extension by original length. So if we rewrite this formula, you will get FL by A del L. This is very important. Okay. So in general, if the Young's modulus is more, means the curve is more steeper. Yes. Okay. For meaning that even for small amount of extension, you need more force. Okay. This understanding is very important. Okay. No, it does not. Yes. Yes. It depends on the molecular bond strength. Okay. So, but metals will be close. If you take two metals, they will be close to the together. Then, if you take metal and wood, that is sure. But each material will be different. Okay. So, uh, by Young modulus, we are addressing the stiffness of the material. Okay. So, low modulus means flexible elastic material. Okay. So, Young's modulus translate to stiffness of the material. So low meaning like more like elastic. So low Young modulus is you can stretch it easily, flexible. Okay, elastic materials. High means hard. Okay, for example, diamond, steel, ceramics. I hope you get the idea for Young's modulus. Yes. Okay. Yeah. Is it clear, sir? So this rubber band is called a non-linear material. We can calculate, but problem is you cannot plot a reasonable graph from it. It will go like this, blah blah blah. So Young's modulus, you will not, it will never obey for Hooke's law because you don't know when it will come back, when it will not come back. For for rubber band materials like rubber band, you can do only ultimate tensile strength until when it will break. Okay. Yes. Yes. Is it clear, sir? There is one more problem with materials like rubber band is the area of cross section is also not uniform. That's why it's very difficult to plot stress and strain. Okay. Yes, sir. Yeah. Okay. So we have two more things to do. One more thing belongs to syllabus. Other thing is not exclusively belong to syllabus, but often asked in question. Okay. So one, how do we design an experiment to calculate the Young's modulus? Experiment. Okay. So now we have the formula F equal to AL by, sorry, F L by A delta L. Okay. Tell me what are the instruments that you will need. Okay. So we need a wire. Mm, Then super. We need a load, or we need to measure some kind of measuring the load. So we need to have mass. Okay. Uh, then what else you want? Super. Okay. So first tell me what are the materials, then we will go to the instruments. So we need wire, we need load, we need mass. Anything else we need? I think that's all. No need. Okay. So these are materials. Okay. Sir, this is very important for practical. Also your paper 5 in A11. Okay. Second, what are the instruments we need, sir? Okay. So we need a ruler. To what quantity? Measure what quantity? So L and delta L. We need to measure both. Then, okay, that's stand that we will finalize. When what are the instruments? What are the quantities here? Super. So we need top end to measure the mass, ultimately to measure the load. Okay. But how do you measure the force here? Can we use Newton meter or force meter? Yeah. But we need a no problem. So we need Newton meter or force meter. Okay, sir. So how about area of cross section? But wire is too thin enough. So we need a micrometer or a screw gauge. By the way, do you know how to use a micrometer or screw gauge, sir? Okay. Super. Okay, this is to measure the area of cross section. Okay. Vernier caliper is this. Okay. So one is permanent scale, second one is movable on top of the permanent scale. Okay. This is to measure larger distance accurately, such as 5 centimeter, 10 centimeter, something like that. Screw gauge is to measure shorter distances accurately. Okay. Screw gauge is actually, do you know why it is called a micrometer? What is micro? So you can measure 10 power minus 6. That's why it's called a micrometer. Yes. Okay. Screw gauge is, the micrometer is one of the screw gauge. Okay. Yeah. No problem. No problem, sir. Sir, if you measure in the, what is the least amount you can measure in screw gauge? 0.0001, right? Centimeter. Okay. So the centi is already 10 power minus 2. 1, 2. I think you can measure 0.01 millimeter, right? 1 divided by 100. 1 millimeter divided by 100 you can measure. Okay. Yes. Okay. So this is, however, we'll discuss in practical session. No problem. Yes, sir. Okay. So now we need to find force, extension, original length, area of cross section. If you know, then we can find the Young's modulus. Yes, why? So what we will do? So we will take two wires. So one is a wire whose Young's modulus we know. So this is a sample wire. And we will take the another wire whose Young's modulus we want to find. Okay. Now, if we connect the loads same, we know this guy's Young's modulus, so we know how much he will extend. But this is a new wire, it's going to extend some new, right? So at each point for different load, we'll mark the extension. So you will have two equation. So y equal to y1 equal to, so f1. By the way, this L and A, they are not going to change. So you can keep them as a constant. Ratio of A by L. Okay. So K1 F1 by delta L1. Okay. The second material is y2 equal to K2 F2 by delta L2, right? So this K1 and K2s are constant, which we can figure out early. So we can write y1 divided by y2 is equal to f1 divided by delta L1 divided by f2 divided by delta L2, right? So we are choosing the weights, right, sir? So we will choose f1 is equal to f2 in such a way. So what we can do, we can cancel with these two. Yes. Only these two quantities are going to change, right? So you can rewrite this equation y2 equal to y1 into delta L2 divided by delta L1. That's how you find the Young modulus of unknown wire. Already know. This is how we find. Yeah, they will give some sample wire. So they will give sample wire and there will be a note in the sample wire. This wire's Young's modulus is this. Yes. Okay, sir. So this is how we. Okay. Mm. Yes. Can we go to next page, sir? Yes. Okay. So now this is not exclusively there in syllabus, but this been asked more than 10 times in past papers. Okay. So problem set for spring constants. Yes. No, we done with concept for stress and strain. Okay. So, sir, is it clear what is spring constant, right? Yeah. Okay. Now let's say that we take a wire or spring, whatever it is. Okay. This has spring constant K1. Okay. Wow. Now let's say that we have four or five springs, same springs. Okay. For simplicity, we will take only two. Okay. Wow. So first problem, if I connect both springs next to next, what will be the final spring constant? Resultant spring constant. Okay. Second problem, if I connect both simultaneously, what will be the resultant spring constant? Do you understand the problem, sir? Yeah, that's it. In both cases, we are applying only one force. If you want, I'll put a force load. Okay. Super, you are close, but exactly opposite way. Okay. Very close, very close, very close. Yes. So, but we have to, it's not that easy to solve this one. We have to mathematically approach it. Okay. So, first case, we will take two springs in series. Okay. Wow. We know that F equal to Kx. Right. For both spring, we are going to apply the same load. Remember, sir, the springs are massless. Otherwise, for the second spring, sorry, for the first spring, mass of the spring also we have to include in the load. Okay. So, we always assume springs are massless. Okay. Okay. We know that F is Kx. Both of their spring constants are same. K. Okay. Now let's say that F is the load we apply here. For spring 1 and spring 2, it's going to be same load. So what would be the total extension? Yes. So the total extension, okay, is equal to x1 plus x2, right? But the load are same. Load is same. So, sir, F by x is K, right? So F by x is equal to no. Okay. So we will take x equal to F by K. This one. Okay. So instead of S, I'm going to take F by KR. What is KR? Resultant spring constant. Okay. So F by KR is equal to, instead of X1, F by K1. Instead of X2, F by K2. We are applying the same load, so you can cancel out. So 1 by K resultant is 1 by K1 plus 1 by K2. For series. No problem. Okay, sir. This is for series. Would you like to try for parallel by yourself? Yes, but clues, not extension. Nice. Okay, I'll give a clue. Try the load. Okay. So, so if we take same spring and put them side by side, okay. So the load experience. Hmm, yeah. So the total F will be whatever the load experienced by spring 1 plus whatever the load experienced by spring 2. So F equal to F1 plus F2, right? What about the extension? Can you see that the total extension is equal to x1 equal to x2 because they are parallel, right? Okay. So we know that F equal to Kx. So F, I'm going to write K resultant into X equal to F1 K1 X plus F2 K2 X, right? So I'll cancel out all the X's. So what you will get? K resultant is K1 plus K2. Yes. First case we were eliminating springs. Second case we are eliminating extension. Okay. There are okay. Note down and then I'll tell you. So there are three this series and parallel problems in our ASA level together. Okay. So one is resistor. So in series R equal to R1 plus R2 plus R3. Okay. So in parallel 1 by R equal to 1 by R1 plus 1 by R2. Okay. Then we have capacitors. This you will learn in your A level. In series, 1 by capacitance is 1 by capacitance 1 plus 1 by capacitance 2. In parallel, yes, spring constant. In parallel, C is C1 plus C2. Then springs, spring constant in particular. Okay. In series, springs are 1 by K1 is equal to 1 by K2. Sorry, 1 by K equal to 1 by K1 plus 1 by K2. In parallel, so KR equal to K1 plus K2. So I draw the series here. Okay, sir. Can we do a little more complicated problem? Okay. If one spring constant is K, find the spring constant of the following. Yes. Mm. Super. 1.5K. Yes. Okay. So I assume how you would have worked out is, so this is K, this is K. So the resultant is 2K. So this is 1K. So what you will have is 1 by 2 plus 1, 1 by 1. So this is 1 by 2 plus 1 by 1, right, sir? So you have to 2 by 2. So 3 by 2k. Okay. Your 1 by k is 3 by 2. What should be your k? Hmm. K is 2 by 3. Your resultant k is 2 by. Okay. So we should not make these mistakes. Chuma for fun. Yes, no problem, no problem. Yes, sir. Okay. So here is an actual question. So 9702 11 N J 13. Question number 23. Okay. So all the springs have same spring constant. Which arrangement has the largest extension? This is a question. Okay, sir. So this is 2 Newton. A. This is 1 Newton. B. This is 6 Newton. C. This is 8 Newton. D. Okay. Question is which has large extension? Yes. No need. All the spring have same spring constant. Super. Okay. But can you see C and D? They are you can eliminate, but C and D are comparatively higher loads than 2 and 1. You are good. You are good. But we should consider the loads also. Okay. Mm, okay. Elimination. Super. Actually, A is the answer. Okay. Yes, sir. Elimination is easy to do, but since all the spring constants are k, we can just find the spring constant. Then we can find the extension. Okay. For example, in this case, it will be 1 by 1 plus 1 by 1. So 2 by 1, right, sir? So spring constant will be 1 by 2. So 0.5k. Here spring constant is half. By the way, if you have number of springs, equal springs, you can just divide it by the number, spring constants. Okay, for example, in this case, 3 springs. So you can divide spring constant by 3, 0.3k. Okay, here 2 springs, so 2k. Here 3 springs, so 3k. So do you understand how it is 0.3k? Yeah, because it's 1 by 1 plus 1 by 1 plus 1 by 1 is 1 by k. So it's 3 by 1 is 1 by k. So k will be 1 by 3. So 0.3k resultant. Okay, sir. So here 2k, it's 3. Yeah. So now we have found their spring constants. Now force is there. We have to use F equal to Kx, right? So for A, so okay, F equal to Kx, X equal to F by K. Okay, sir. For A, F is 2 Newton. So 2 by 0.5 K. So what you will get is 4, 4 by K. Okay, sir. Now for B, you will get uh, 1 divided by 0.3 K. So you will get 0.3 divided by K. For C, you will have 2k. So 6 divided by 2k. So you will have 3 by k. For D, you will have 8 divided by 3k. So what is 8 divided by 3, sir? 6 divided by 3 is 2. So 2.5, maybe approximately 2.7. So 2.6 divided by k. Out of which is bigger? 4 divided by k. So A is bigger. Okay. So if you yeah, if you cannot assume what is the value be k, you can just take k is 1 because all the swings are the same. So you can just take k equal to 1, then you will get 4, 0.3, 3, 2.6. Yes, you can just open. So here is the answer. Okay, sir. See, this is actual past paper. So we have multiple questions for spring constant that I'll give you in this guys. Okay, question banks. Okay. So we'll do just one more question for our understanding, then we'll move on. Okay, so this is 9702 13 ON 14. Okay, question number 25. So we have two springs of spring constant. This one is K1 4 kilonewton meter inverse. This is K2. This is 2 kilonewton meter inverse. Okay. And we are adding 80 Newton load. Okay. What is the total extension? So four options: 1.3 centimeter, 4 centimeter, 6 centimeter, 60 centimeter. Yes, sir. Yes, sir. What is the total extension? Exactly how you will make a mistake. Yes, 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 yes. Hmm. Okay. Look at the unit. Sir. Okay. First, what is the total spring constant? Okay. So it will be 1 by uh, K1 plus. Yeah, we don't have 1 by K. That's why it's explicit. Okay. So 1 by 4 plus 1 by 2. So this will be, this is 4 by 2 by 4. And you will get 3 by 4. So 4 by 3 is spring constant. So K 4 by K is 4 by 3 kilonewton meter inverse. Okay, sir. Now we know force is K into X. So we want X. So force divided by K. So 80 Newton force. So 80 Newton divided by 4 by 3 kilo Newton meter inverse. Okay, Newton and Newton will cancel. So this 3 goes, then 3 into 80 divided by 4. 24 or 80, 3 into 4, 60. So 60 meter. Is it 60 meter? Yes. There is a kilo. Can you see there is a kilo here? If this kilo come to top, then it will be 10 power minus 3. So I can convert this 10 power minus 3 into 60. So what you will get? 6 into 10 power 1, 10 power minus 2. So 6 into 10 power minus 2 meter, which is, yes, 60 into 10 power minus 3 meter. Okay, here is 60. 1 0 extra you have. 10 power 1, right? Here is 10 power minus 3 meter. What is 6 into 10 power minus 2 meter? 10 power minus 2. What is 10 power minus 2? 6 centimeter. Okay. So if you forget the kilo here, or if you forget to convert the Newton into meter, we will right there fell in their trap. Yes. Okay. Yes, sir. Is it clear? Yes, sir. Okay. So next we shall go to elastic and plastic behavior. You want a break, sir? Yes. So we have cover maybe 15 or 20 more minutes. Mm. Yes, sir. Okay. So now we have 6.2 elastic and plastic behavior. So remember from the graph that we said 2 points are not there in the syllabus that time. They are here in a different name. Elastic limit. Okay. And elastic deformation. So we have to understand 3 words. What is elastic deformation? What do you think? What is elastic deformation, sir? No. Elastic limit is hooks. What is elastic deformation? Meaning that, yes. So changes can be undone. So if you remove the load, you will come back to original position. Okay. So I'll give the exact definition. Okay. Temporary change to object shape or size when it's applied. But if you remove the force, the material fully returns to its original form. Okay, that's elastic deformation. Plus plastic deformation. No. Plastic is permanent. Changes cannot be undone. No. Elastic is, yes. So plastic deformation is permanent change. Okay. It will try to come back to its original position, but it will never be original. Sir, we call rubber elastic because if you stress, they'll come back to original position. Okay. We call some objects plastic because they are permanent shape. That's what we call it as a plastic deformation. Okay. Elastic means it should come back. Plastic means it will never come back. An elastic limit is until when it can come back, it's elastic limit. Yes, yes. So that's what elastic limit is, little bit more than Hooke's law, elastic limit of proportionality. Now I think you can clearly understand the difference between limit of proportionality and elastic limit. Okay, until which the changes can be undone, or the material returns to original shape. Okay, yeah. So remember that we had this 4 sections in graph. Okay, so in general, let's say that I take a spring. If I put 1 Newton load, it extends to, let's say, that 1 meter. The extension is 1 meter. So in general, what we know work done is force into distance, right? So in this case, force into extension. Okay, but problem is, despite of it extends 1 meter, it's not just completely 1 meter, right? Already there was some length, and then it extended some. Okay, so this is literally half, only half. Okay, yes, yes. Okay, so the total distance it has extended, the total distance might be 2 meter, but the extension is just 1 meter. But the rough idea is force into distance. Okay, now extension is the distance, force is given. So in any given point, if you multiply these two, you should get the work done, stretching this one. Okay, so from this point to this point, I want all the work done. So how you will find it? Find the area under the curve. Okay, yes. So if you find the area under the curve, area under the curve of force versus extension, yes, is work done. Okay, sir. So till, so you clearly said it's still limit of proportionality. Then how the shape will look like? Triangle. So what's the formula? So work done is half pH. So in this case, half Fx. Okay. Yes. Yes. Elastic potential energy. Stored. Okay. If the deformation is plastic, it's not. Okay. If I take this point, the work done is F into X at this point. If I take this point, the F into X at this point. What is from moving here? Yes. What is moving from here to here? That we have to collect all the point, right? What is that? Area under the curve. Yes. Okay. So if they asked for particular from this extension to this extension, you just find the area under the curve. Okay. But there is a trick. Let's say that if a graph is like this, force is here, extension is here. Okay. And okay, it look like this. So if I invert this graph, it will look like this. Can you see? Can you see? Yes. Now you should not find the entire area under the curve. What is the area for extension is only this. Because this is the original length, right? And this is the final length. So only you should find the area under these circumstances. This one now. Yeah, it is possible. When in this graph, when is force is 0? Okay. So meaning that you just choose your axis so that extension starts from here. That's all. Okay, or this is the original length. Okay, is it clear, sir? Nice question though. Hmm. Is this clear, sir? Now work done is half Fx. If spring constant is given, that's all. So work done is half kx square. Okay, that's all, sir. Elastic and plastic behavior. So deformation of solids. Yes. Okay, but sometimes they'll twist for graph like this and ductile and brittle and spring constant. So that, yeah, that we should be a little careful. Uh, 1 minute, sir. I'll see. Okay. So, can we do one question, sir? Young's modulus. So we'll do 2 or 3 questions and then I'll give you question bank. Okay. By the way, when okay, so that we'll discuss later. Yes, sir. Okay, so this question is from 9702 13 October November 13. Okay, question number 22. Okay, sir. So there is a lift. It is supported by two cables. So each cable are 20-meter length. Okay. Each cable consists of 100 parallel steel wires. Okay. So it's not a single cable. Each cable is 100 steel parallel wire. Right? Okay. Each wire has a cross section of 3.2 into 10 power minus 6 meter square. So steel wires. Okay, sir. So this Young modulus of steel is 2.1 into 10 power 11 Newton meter power minus 2. Is it clear, sir? Yes. Which distance the lift move downward when the mass of 70 kg man steps in? Do you understand the question, sir? Yes. Super. This is how you should address the question. What blah 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 sorry steps aside, what we want. Okay. Yes, try. Please try. Yes. Yes, sir. Yes. Each one they have 100 steel wires. Mm. No problem, no problem. Mm. Uh, 0.010 millimeter, 0.020 millimeter, 0.10 millimeter, 0.20 millimeter. Option B, tell me what formula you have worked out, sir. Okay. Mm. Okay. Mm. Oh, you use that method. Okay. 17 to 9.81. Okay. 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 So if what's the value spring constant you found as? Okay. But that's not necessary because Young's modulus is given, right? So you can directly use this formula. Y equal to F L divided by A delta L, right? So we have to find only delta L. So F into L divided by A into Young's modulus. Okay, sir. Now F is, as you said, right, 70 into 70 kg into 10 Newton kilogram per meter square. Sorry, meter per second square. Okay. So we can call it 70 into 10 Newton multiplied by length is already 20 meter divided by area of cross section is 3.2 into 10 power minus 6 meter square, right? But how many wires? Plus another 100 here. So 200. What is the Young's modulus? 2.1 into 10 power 11. So work out the answer, sir. You get the idea, sir? How simple is it? Yeah, no problem. No problem. Mm, no problem, sir. Okay, meter or centimeter? Meter. So you would have you would have got this into 10 power minus 4 meter. Okay. So we can ignore this. Okay, just 1 into 10 power minus 4 meter. So I'll write it as 1 into 10 power minus 1 into 10 power minus 3 meter. So 10 power minus 3, I can get it as millimeter. 1 into 10 power minus 1 is 0.1. So option C. Yes, sir. See, any physics problem, try to find one formula that accommodates all the variables and what you have to find. If that is not possible, then we go to two-hand problem. Find one formula and find another formula which involves any one of the variable in this one. Okay. Otherwise, that's an unnecessary step. But good idea though. Just yes. Okay. No problem. No problem, sir. Yes, sir.